All right. So this is your outline for your chapter. I'm going to skip these in the future. I'm just pointing out what it is now because you may not have realized. So let's talk about atoms and how they're composed. Does anybody know what atoms meant? What the word actually means? Comes from atomos, which means indivisible. You can't break it down anymore. Is that quite right? Arguable. So we can break down atoms into further particles, right? And those particles are going to be protons, electrons, and neutrons. These are what are called subatomic particles. So they're going to be smaller than atoms. They're going to be what atoms are composed of. Okay. Now remember that when we get down to protons, electrons, and neutrons, a proton doesn't have the properties of gold or silver. Okay? They're what compose and make up these things. It's actually the structuring of these items that gives us the elements gold, silver, etc. Okay? All right, so the protons and electrons, these are the charged particles. Protons are positive, electrons are negative. Neutrons are going to be neutral, as the name indicates. Protons and neutrons have a mass of AMU, atomic mass units, of 1. Okay? Electrons, on the other hand, have a mass 10,000 times lower than a proton or neutron. We typically just call it 0 and don't worry about it. Right? So, does anybody know what electricity is? You're all familiar with electricity, right? Okay, hopefully. We're heavily using it right now. So electricity is actually just moving electrons. You notice the naming of these things is very consistent, isn't it? I know. You'd always been playing around with electrons. You just didn't realize it, did you? Okay. So again, when we talk about electrons, keep in mind that if we have a flow of electrons, that is actually electricity. All right. So overall, atoms on the periodic table typically have no charge, and this is because the number of protons on the periodic table is the same as the number of electrons for those atoms. And that gives you no overall charge because they have the same positives and negatives, right? One of the easier ways to think about these things is this is basically just accounting for electrons. Okay? We're just balancing our checkbook for atoms. So the structure of an atom, the protons and neutrons, these are going to be clustered together in what's called the nucleus. The nucleus is in the center of your atom. If you want an idea of the size and structure, think of a tennis ball being placed out in the football field. That right there would be the size of the nucleus to the first orbital for electrons. Okay? So the size of the atoms, the nucleus is very, very small size-wise. The electrons are going to be dispersed throughout the area around the nucleus. They're sort of popping in and out of existence all over around that nucleus. Okay? Okay. So have you guys heard models of the of atoms before? Probably, right? Okay. So did you guys ever see the one where they have the electrons going around in orbitals? Is that the one you were all taught? Yeah? Was anybody taught one where the electrons are popping out of existence? No? Okay. Okay, so the electrons do not orbit the nucleus in orbitals at all. That is not correct at all. It is not like planets around the sun. However, it's a very useful mental image, and it makes things real easy for people to understand because it looks like something we know, right? Okay. What they do is there is orbitals, but they don't circle around the nucleus like planets. What the electrons actually do is they pop in and out of existence, pop, 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 around the nucleus, and the orbitals are where we have a very high chance of finding them. Okay? You can think of them more like electron clouds. Okay? So it's like a cloud around a nucleus, a center. Anybody ever seen those nebula? No, where it has like the star and then there's a cloud around it? Yeah, it's kind of like that. Okay, that's actually a better mental image to have. Okay, so again, these electron clouds, those electrons are constantly going to be moving. They're going to be essentially impossible to actually nail down where they are. And so we just have a probability of finding them. Now, note that this means that the atoms are actually almost entirely empty space. Something like 99.9 something after that empty space, depending on the atom. Okay? And that means that you right now, the volume you occupy, is 99.9 something percent empty. So you occupy less volume than nothingness does. By a lot, right? In fact, if we round to the first decimal place, do you know what volume you occupy? If we were to round to the first decimal place? Nothing. You can be rounded off from existence. Isn't that just amazing? So, when we look at atoms, 99.99% of the mass exists in an area that's about 0.1% of the volume. Okay? And that's the nucleus. The rest of it is just negatively charged particles that have almost no mass, occupying a bunch of space. Right? When you touch something, what are you doing? Are your atoms coming into contact with other atoms? No, you just pass right through if that was the case. So what's actually happening is your electrons are repelling the electrons of the object you're touching. And so you never actually come in contact. You actually start repelling, and then you can't force it any further. Right? If you could apply enough pressure, you'd actually overcome that, shoot a bunch of electricity off it, and then you'd actually cause fusion. Okay? And that would be overcoming that, and that's what the sun does. It does fusion, provides a bunch of energy and light, right? Fantastic. Okay, does anybody have any questions about what an atom looks like? All right. So let's talk a bit more about the structure of an atom and the components of an atom. Now remember that even though these are very, very small, these are matter. This is what all matter is composed of. Okay? They build up to make matter. And so most of the mass of an atom, again, is going to be in the nucleus. This is going to be where the protons and neutrons are located. That's actually what is composing that mass. The vast majority of the mass of the atom. The mass of an electron is about 2,000 times-ish less than the proton or neutron. And so we typically just ignore the mass of the electrons because it would take 1,000 electrons, 2,000 electrons to actually add up and give us the mass of a proton, right? There aren't any elements on the periodic table that even come close. Okay? Remember the atomic numbers on the periodic table? Hydrogen's 1, helium's 2. Okay. Those are actually the number of protons. Because they're neutral when we're talking about them on the periodic table, those are also the number of electrons. Okay? So we actually don't even get up into into the 200s, do we? Yeah. So we're normally dealing with numbers of electrons in the 6 and 12s, right? Almost nothing compared to the number that would be that we need to get for a full mass unit. Okay. So these are the different symbols. Electrons, their symbol is E minus. Can everybody see that okay? Okay, E with superscript minus. Protons, normally people just put P, but if you want to be very specific, you can put P plus. Okay? And that really lets people know, hey, that's a proton, positive charge. Okay? And then this right here is the neutron, and this has an N for neutron. And if you want to really make sure people know, you put it to the 0 power. And that's because it has no charge, right? Charge is 0. Okay. And so this is, again, the electrical charges. Electrons are what charge? Negative. Protons are what charge? Positive. Anybody know what these charges have to do with? Anybody ever seen a magnet? And they have a plus sign and a minus sign? These are what cause that magnetic to work. So when you're looking at a magnet, it has more protons on one side and more electrons on the other. All right? And that's how it gets its positive and negative charges. Okay? There you go. Yeah. So whenever we talk about these, I'm going to oftentimes use magnets as an example. Okay? Now the relative masses, these are going to be for the electron, 0.0005. These units right here are called atomic mass units. They're a number that's been set based on the masses of protons and neutrons. And so that's why these are listed as 1, and these would be 0.005 here. The nucleus is protons and neutrons. Outside the nucleus is then electrons. I will note that hydrogen actually does not have any neutrons normally. Okay? Anybody ever heard of deuterium and tritium? Like a heavy water reactor for nuclear reactors? Okay. You may or may not have. Tritium's what we're trying to find in the moon so we can do like space missions and stuff. They're making to do fusion with. Anyways, normally hydrogen does not have a neutron. Deuterium and tritium, and we'll get into isotopes later, which is what this is, have a neutron and 2 neutrons. It's the weight of them. So deuterium has a weight of 2. Tritium has a weight of 3. Okay. So the structure of an atom. Again, the mass units are going to be called atomic mass units when we discuss atoms. An AMU is actually 1/12 the mass of the carbon atom. So we would take carbons, we would measure those out, and then we would divide that by 12, and that gives us an AMU. Now carbon has 6 protons and 6 neutrons. And so that's why we end up dividing it by 12 to get what an AMU is. The proton and neutrons are each going to weigh about 1 AMU. In this carbon, it'll be exactly 1 AMU. The mass of an electron is going to be so much smaller that the electrons are considered to have a mass of 0 when we normally talk about this. Because even if we have 100 of these things, we're still only at the 0.1 stage, right? So it's not normally an issue. This right here is going to be, this is lithium metal. As in lithium in your phones and lithium in your batteries, right? Does anybody know what happens when a lithium battery goes and blows up? Why those things blow up? So normally it has lithium ions in your batteries. This right here is lithium metal. This is the neutral one. So what happens when your batteries are mistreated and misused is that you develop lithium metal crystals. Those react very explosively with moisture. Okay? And so that's actually what causes the explosions. Anybody seen the Tesla explosions? Where people are like charging them on really hot or really cold days and they go boom. Okay. That's this. Right there. All right? So this is what lithium atoms look like. They have a very nice crystal structure. That's actually what gives that nice, it's like cubic. Looks like little cubes for the crystals. That's what gives that. And so they're composed of these lithium atoms. We normally represent them as little balls, and those are showing where the electrons would be. Okay, those are little shells of electrons around them. And then we go ahead and subdivide that more, and we peer inside that. And what we would see is a nucleus composed of protons and neutrons right here. And then around it, we would have electrons. Now we've frozen those electrons in space and put actual little dots there, so it's nice to look at. Okay? But see how it has a shading around it, that green shading? Okay. That's actually the probability of finding electrons. Those electrons are anywhere in there. We don't really know. They're going to be popping around and zooming around so fast that it doesn't really matter. Okay? Okay. Like if something's going supersonic, is it really meaningful to say it's right there now and right there now? Not really, right? You just trace the path. Okay? And that's more meaningful. All right, so the atoms of the same element always have the same number of protons. That's actually what sets what element it is. That's what gives it those chemical properties, is the number of protons. Okay? So when we look at carbon, how many protons does that always have? Anybody got the periodic table with them? I just gave it. 6. Carbon always has 6 protons, right? If I had 5 protons, could I be carbon? No, by definition, I could not be carbon, right? Okay, if I had 7 protons, could I be carbon? No, by definition, I can't be carbon, right? And so, always the number of protons tells us what the element is, okay? Okay, it's in fact the adding or removing of electrons to those nuclei that is chemistry, okay? That's what chemistry is ultimately going to be. So, the atomic number, this is actually on the top of the block typically, and it's the first number that denotes everything. It's how the periodic table is ordered. And this actually is the number of protons. There's also a mass number on the periodic table. Can anybody tell me what the mass number would indicate? Kinda. Protons and neutrons, right? Or another way of saying that is the nucleus mass, or the nucleons is another way, in case you ever want to know that. Okay, I know. So you'll notice I'm going to do this. This is called Socratic learning. And what I'm doing is I'm making you try to use your thought processes, your logic, and your critical thinking to develop the next steps, right? Does anybody know how you develop critical thinking skills? Do you do it by parroting somebody else over and over? No, you'll never develop critical thinking skills. So the methodology to develop critical thinking skills is to think about a problem, try to come up with answers, and then see how you go through those steps from somebody else if you're having trouble. Okay, and so right here, again, we're going to have the protons. That is what's going to give an atom its unique properties. Neutrons are neutral, and so they don't give the atom its chemical properties. They don't affect how it pulls electrons in. They don't affect any of these things. You will notice that the number of neutrons, again, does not affect what element it is, right? So could we have a carbon with more than 6 protons? No, right? Could we have a carbon with more than 6 neutrons? Yes, yeah, we definitely can. Anybody ever heard of carbon-13? Carbon-14? Radiological dating? No? Okay, we'll talk about it a little bit later on. Okay, and so right here, this is just an example. Here we have carbon. This is what carbon would look like if we just have pure carbon sample. This is one of what's called allotropes, meaning different arrangements of them. Does anybody know any of the other forms of carbon, by the way? Okay. So we have charcoal. This is pure carbon. Charcoal, or yeah, it looks like charcoal. Okay. You have another form of pure carbon in this room right now? Anybody using a lead pencil? Yeah. Okay, so that's not actually lead, that's graphite. That's another form of carbon. Okay. Anybody have diamonds? Don't raise your hand. Somebody might get greedy. No. Diamonds are another form of pure carbon. Okay. So this right here, if we zoom in, we're going to see that there are atoms in this. And what we see here is that it's an atom with a nucleus and that has electrons zooming around. Is that picture ever to scale on any of my slides? No. This electron cloud here, if I was to represent this way in this size, the nucleus would be so small that you couldn't see it. Okay? And so every time I do these, I have to give you something that's totally out of scale. Just not even close. Right? You wouldn't be able to see anything about the nucleus at all. It wouldn't even show up. So I'd have to zoom it so you'd be able to see it into something resembling the size of this building, right? So, yeah. All right, so the mass number, this is that number. If you're ever looking at this sort of representation, this is called a symbolic notation, you would see the mass number right here. This is the number of the protons plus the neutrons added together. This is what that number was when you were saying like carbon 13. The mass number is 13. Carbon 14, the mass number is 14. Uranium 235, the mass number is 235, right? Okay. And so that is going to be the number of protons plus the number of neutrons. If you ever need to figure out the number of neutrons, there's a very easy way to do it, and that's by just subtracting off the atomic number, right? Which is the number of protons. Okay. If they don't give you the atomic number like this right here, see how that has 6 on the bottom there? That's the atomic number. That's the number of protons. So if you're going to do it completely correctly, it would be, this is the proper terminology. It would be a symbolic notation. You'd have your mass number as a superscript in front. You'd have your atomic number as a subscript in front. Then you'd have your atomic symbol. That would be that symbol on the periodic table. Note that the atomic number and atomic symbol tell you the exact same thing. There is no actual new information between those two. Okay? If you have an atomic number 6, that means automatically it has to be carbon, right? If you have carbon, the atomic number has to be what? 6. Yeah, it can't be anything else. Automatically done. Okay? The mass number can be different because you can have different numbers of neutrons. Right. This right here would be the charge. In this case, we have 0, so we don't have to write it. Okay? If you had a charge on this, positive or negative, that's where you would write the charge. Okay? And that would take a different number of protons and electrons. If you have the same number, you have no charge. Okay? All right, so oftentimes what you will see is that chemists get lazy. Most scientists don't like writing out more than they have to. And so most scientists will not write the bottom number. Why can I do that? Yeah, I don't need the carbon and the bottom number, do I? Yeah, they're the exact same thing. So if I have carbon, I know it's 6. Yeah. If I don't know off the top of my head, grab a periodic table. You can look it up, right? And so, yeah. Most people don't write the bottom number. Determining the numbers of subatomic particles in symbolic notations. First, step 1, find the element on the periodic table. Step 2, use the atomic number to find the number of protons and electrons. If they haven't indicated anything else, then it's neutral. The number of protons, the same as the number of electrons. Okay. Use the mass number to find the number of neutrons. Write the element in symbolic notation. All right, so let's go ahead and talk a bit about isotopes. So atoms of the same element, these can have different number of neutrons. When they have different numbers of neutrons, we call those isotopes. So again, you can have the same element, carbon, with multiple different masses, and those masses denote differences in numbers of neutrons. Okay. Anybody ever heard of uranium-235 and uranium-238? No? Anybody ever heard of depleted uranium before? No. That's actually kind of sad because we put so much depleted uranium in the Middle East now because of the shells and the bullets that we've actually raised the entire radiation level of the Middle East. Yeah. And that's because we've had, 40 years, I mean humanity, not just the United States, but, there's been 50 years of modern military warfare in the Middle East. All of that was depleted uranium shells, so because they're very heavy. So it's pretty crazy stuff. All right. So the atoms of the same element, different masses. Again, these are isotopes. There's several different ways we can indicate this. We can use the symbolic notations that we just talked about right here. Or we can actually say carbon-12. That would be the normal isotope of carbon. carbon-13, that would be the mass number 13 carbon, right? Carbon 14, mass number 14 carbon. All right, so now, when you look on your periodic table, you may have noticed that these dang things have fractions. That's weird. That doesn't really fit in with Dr. Clausen's telling me, does it? Okay. I haven't talked about any fractions, have I? No. In fact, if I'm looking at a single nucleus, does a fraction make any sense? Could I have a 12.5 carbon? Could I have a half of a proton, half of a neutron? No, that doesn't make any sense, does it? And so what I'm looking at then is I'm actually looking at average masses. Or more specifically, I'm looking at weighted averages. Have you guys ever done anything with weighted averages in your math classes before? Yeah, kind of. Yes, but kind of don't remember anything. Okay, that's fair. That's fair. So most of your grades are probably calculated as weighted averages. Your grade in this course is calculated as a weighted average. Okay? And so what that says is that based on the number of points or the importance of it, it gets a weight, right? So for example, 50% of your grade is exams. Okay? And so when I look at my grade, 50% of it is composed of the exams, isn't it? When I look at the masses on the periodic table, what I'm going to see is that I take a sample of that substance from this solar system, okay? And then what I do is I take the average of all the carbons in that sample, and that gives me a weighted average based on the amount of each form of carbon, okay? And that's why the mass on the periodic table for carbon is very, very close to 12. There's very little of the other forms of carbon in this solar system. Okay? For example, the abundance of carbon-12 is basically 99%-ish. And then about 1% of our sample of carbon is going to be carbon-13. And then the next form of carbon is like a trillion to 1, right? There's almost no of that carbon at all. Okay? And so the vast majority of our samples of carbon when we're looking around Earth or this solar system is carbon-12, right? Okay. If we start looking around on the periodic table, what we can notice is that some of these isotopes are actually in large abundance. Okay? If you start looking over at like chlorine and bromine, you see that they actually have numbers that are close to 0.5s. And that means that they have different isotopes that are of large abundance, that there's a significant amount of, like 30% of this sample is this other isotope, right? Okay, so radioactivity and radioisotopes. Anybody ever heard of radioactive? Yeah? Yeah, hopefully. If you haven't heard of it, that's a shame. It's a shame. Okay, so the energy given off spontaneously from a nucleus of an atom is called nuclear radiation. This happens typically when you have atoms that are not stable. Their nuclei are not stable, and so they slowly break down over time. And the nuclei of some atoms are going to be unstable atoms, and they can be radiate, and this is going to give off energy. This was actually discovered because you put these atoms near a radio transceiver, right? Like I'm listening to the radio, and they'd actually go crackle pop, okay? And so they were literally active on the radio, right? I know. All right. And so elements that emit radiation, again, are going to be said to be radioactive. That radiation is going to be a form of energy that we can get from natural and human-made sources. In 1896, Henry Becquerel actually got an exposure on a photographic plate in the dark by placing the plate next to a rock that contained uranium. And this is actually how these studies were first done in the beginning. Is essentially you would take an element, and if it's radioactive, what will happen is it will develop on a photographic plate because it's releasing its own radiation. Now, the majority of the radiation coming off of these things is just electromagnetic radiation. Does that sound threatening? Ooh, You're all being bombarded by electromagnetic radiation. Can anybody point to any sources of electromagnetic radiation in this room? Death ray. Yeah, so that's actually the most powerful source of electromagnetic radiation in this room, right there. Okay, electromagnetic radiation is light. Okay, the vast majority of electromagnetic radiation is light. That's also Wi-Fi signals. It's also gamma rays, X-rays. There's a bunch of different types. Okay, we'll go into those a little bit later on in another chapter. But radioactive substances release radiation. Most of that radiation is electromagnetic radiation. Okay. Okay. And so most naturally occurring isotopes have a stable nucleus, and so they will not be radioactive. And this is the majority of the atoms in your body. This is the majority of the atoms around you. However, did you guys know that you're all radioactive? Yeah, you've been sitting there and exposing me to radiation all dang day. My goodness. Okay, there's actually a really funny thing with the federal government that we'll talk about in just a second. But humans have a radioactive form of potassium. They absorb it whenever they eat something with potassium in it. You need potassium in your diet. And so you do have radioactive isotopes you incorporate into yourself. As long as you live, you're going to be radioactive. Okay? It's a very low level radiation. It's not really anything to worry about. And frankly, it doesn't matter. Now, having said that, did you know that during a nuclear incident, there is no safe limit of radiation, and you must dispose of any level of radiation on any sample? So if a nuclear incident happens, by federal law, they should take you and they should dispose of you. All the humans in the area. So, whoa, huh? Because there is actually no lower limit in federal law. Isn't that just mind-blowing? So, do you know there's nuclear power plants in Tennessee? So right now, by federal law, if any of them have any incidents at all, which could be as simple as them detecting higher radiation on the power plant, which could be as simple as like cosmic particles came and we had slightly elevated radiation. Could not be anything to do with the power plant. All the humans in the area should be disposed of as nuclear waste. Sometimes. All right. So most isotopes are actually stable. Isotopes that emit radiation are going to be called radioisotopes because they are radioactive. The process of these nuclei breaking down and becoming more stable nuclei is called radioactive decay. It happens within the Earth all the time. It's actually why there's geothermal energy and the center of the Earth is hotter. Okay? Is radioactive decay is happening, and then the Earth doesn't allow that heat to escape. It actually recycles that heat and warms up over time, over the billions of years. It also is why, for example, there is radon that seeps out of the Earth. Anybody ever heard of radon before? Let's take a survey real quick. I've heard of radon. I have not heard of radon. Okay, wow. Okay, so there are states in the United States and throughout the world. There are countries that are called radon states. There are places where radon gas seeps out of the Earth because it's a gas that comes off when you have nuclear decay, okay, or radioactive decay. And radon is radioactive. It's a radioactive gas. And so if you put any basements into a building or you dig out the bottom of a building and it doesn't have really great ventilation, you will actually breathe in radioactive substance. It will give you, over time, a very high chance of getting cancer, lung cancer specifically. And most radon states require a test to be done anytime you sell a house, and then you would give that test result to the person that buys the house. And it's actually fairly easy to fix as long as you put in a ventilation system to blow the gas out. Tennessee is the only radon state I have ever seen in my life that does not have those rules and just doesn't talk about it. And I think I know what it is. I think it's because you guys have so much water in the soil and it's so high that nobody builds basements. Everybody builds up on stilts, right? Or blocks. And so if you have blocks and then you have some ventilation under your house, it's not an issue. But it's kind of funny because I've never seen it mentioned by anybody that even has basements.
Could the water in the soil help keep the gases
No. Yeah, it'll just percolate through. Most states that don't have radon, what they have is like a very large granite slab that those states on. And so it can't go through the granite slab, and it just goes out the other sides to the other states. Other than a few states that are like that, they're not radon states. The Rockies has a lot of them. Yeah, because they're on like tips of giant mountains. So, not as much radon. But yeah, it's a weird thing. And it's something that like nobody in the state is aware of. I've never seen that before. Also a plumb bob. Anybody know what a plumb bob is? I swear that like the entire state, they never got introduced to plumb bobs, and every building in the state is uneven. Like this building is uneven. There's like 2 right corners in the whole state. And it just drives me nuts. Every single room.
They use them for putting up the new poles for power lines.
Exactly, because you want it to be even, right? Yeah. Maybe they're learning, probably. Yeah. I guess I haven't seen a lot of the newer buildings that haven't been renovated stuff. So, yeah. The new buildings might have. Okay. Anyways, now that we got my OCD out of the way. All right. So all of the isotopes of elements with atomic numbers 83 and higher are actually radioactive. Some of the lower elements do have radioisotopes. For example, potassium, we had just talked about. But anything above the atomic number 83, all radioactive, okay? Anybody know what atomic number 83, where our radioactivity begins for everything? Lead. So lead is the last one that you see that has a lot of non-radioactive isotopes. Okay? The rest of them, it's all radioactive. Right. Now, you can have less and more radioactivity. Some things are radioactive, but half the population goes down every billion years. Okay? Some things are radioactive and half the population is gone within a second. Okay? Some things are a lot more radioactive than others. Now, the forms of radiation. The first 3 forms of nuclear radiation that were discovered are the following, and these are actually how we discovered what an atom's made of and how it's constructed. And so there is the positively charged alpha particle. The alpha particle is actually a helium nucleus that's being shot out at very, very, very high speeds. I'm talking way higher than supersonic. Okay? And that's the slowest particle on this list. It's 0.2 the speed of light. Or a little bit less than that usually. Very fast. We have the negatively charged beta particle. Beta particles are just really fast moving electrons. They're typically moving on the order of like 0.9 the speed of light. Okay? Very fast. Neutral gamma radiation. Gamma radiation is actually light. It's very high energy light. Now, do you want to get hit by gamma radiation? Absolutely not. Okay? You will not become the Hulk. You will, in fact, just have all of your bonds smashed apart by the gamma radiation and be disintegrated. Okay? If you ever wonder why people get at the very edge of a nuclear blast, that like really painful sunburn effect, that's exposure to gamma radiation. Okay? Okay, and so these right here are the different emissions. We have here the alpha. Again, that's a helium nucleus. It doesn't have time to grab the electrons, and so it gets shot out without any of the electrons. Okay? So it has 2+ charge. Here we have a beta, and that's going to be an electron shot out at tremendous speed. And so it has no time to interact with anything, get captured, nothing. It's shooting out there, and nothing can grab it until it slows down. Okay? Here we have gamma. This is just going to be very high energy light, electromagnetic radiation, very high energy though. Okay. This is a positron. Anybody ever heard of antimatter or a PET scan?
Yes.
Okay. PET scan is actually a positron emission tomography. They shoot you with a beam of positrons. Okay. Yeah. And so that is antimatter. When it comes into contact with an electron, it actually annihilates each other and forms energy. Okay? And so both of them stop being matter and go to energy. Poof, gone. And the funny thing is, a tomography is a type of scan. So you know how people say PIN number? Personal identification number? Okay. Saying PET scan is the same sort of thing. It's saying positron emission scan. And it's the correct way of saying things. And so every time a doctor or somebody says something like that, you go, that was so stupid. Scan, huh? Tomography scan. Neutron, this is going to be one of the more common radioactive emissions and one of the more common particles that's going to hit us. These are very penetrative and they're moving very fast. Okay? And so these are what you usually start nuclear reactions with by shooting them with beams of neutrons moving very fast. Smashes apart the other nuclei, causes other nuclear transformations, nuclear reactions. Okay? This is actually, have you guys ever been in a hospital and there's a little radiation sign? Okay, that's called the radiation ward. And what they're doing is they're generating different types of radioactive isotopes at that ward so that they can use them as different identifying, like to do PET scans. Okay, as a source to do a PET scan, they can use them to label different molecules and then have you ingest those and follow those through your tract, that sort of thing. They typically have a neutron source they're doing that with. That's by far the most common. Okay. Anyways, we'll pick up here next time. You all have a wonderful day. Have a wonderful weekend. I'll see you next week. Remember, labs are next week. Labs are starting next week. We'll do the contract in person. Okay. Fantastic. We'll finish this chapter up next time. You all take care.